Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are going to start our discussion on chapter 22, which is concerned with the chemistry of Enolate and ions. Okay, before we start the session, let me make a few announcements. I want to remind you of the online midterm online survey that I sent out yesterday. The deadline is tomorrow, that is Friday, March 29 at 11 p.m. I also want to remind you that the homework assignment for this week, which is our chapter 21, is due on Sunday, that is March 31st, is that right? Okay, at 11 p.m. Oh, also, I do want you to mark your calendar because the next class exam is less than 2 weeks from now, which is Tuesday, April 9. So because of that, we are going to have 2 online sessions next week. There will be one on Wednesday, that's April the 3rd at 8 p.m. Then there will be another one for the review on Friday, April the 5th at 8 p.m. So I will send you a reminder next week. Okay, so let us start with our discussion today. Ayana, can you read for us what we are going to do today?
Today's topic, fire concepts, reaction of Enolate and Anions, and halogenation of aldehyde and ketones via Enolate and Anions, halogenation of carboxylic acid, alkylation, malonic ester synthesis, and ketoacetic ester synthesis.
Okay, thank you. Okay, so those are the topics that we are going to cover today. We are going to discuss the malonic ester synthesis, which relates to the chemistry of Enolate anions, and also acetoacidic ester synthesis, also relating to the chemistry of Enolate anions. Okay, as usual, I want to share this slide with you, which is the list of learning outcome objectives. Upon completion of this chapter, you should be able to perform all of the concept and all of the topics and concepts that are listed on this particular slide. So you should use this as a study guide for studying for your quizzes and your exam. Okay, now the question now is, what are Enolate anions? What are Enolate anions? Enolate anions are carbo anions, alpha 2 carbonyl functional group, Okay, carbo anion, in other words, negatively charged carbon atom, that is attached to a carbonyl functional group. We could also define enolate anions as conjugate bases of enols. Okay, so we could give two definitions for enolate anion. One, that they are negatively charged carbon atoms that are attached to carbonyl functional groups, and the other is they are conjugate bases of enolate anions. Let us say, for example, we have this. If we have this molecule here, that is a ketone. And then we also know we have this carbonyl functional group right here. This carbon here, remember, you notice that we say alpha. This carbon here, the carbon that is attached to the carbonyl is referred to as an alpha carbon, using the Greek symbol alpha. The carbon that has a 1,3 relationship to the carbonyl function here, we say that is a beta carbon, also the Greek symbol. And the carbon that has a 1,4 relationship to the carbonyl, we say this is a gamma. So this is gamma, beta, alpha. So therefore, those hydrogens that are attached to the alpha carbon will be called what? What type of hydrogen? They will be called alpha hydrogen. And similarly, the hydrogens attached to the beta carbon will be referred to as beta hydrogens, and those attached to the gamma hydrogen will be referred to, those attached to the gamma carbons will be referred to as gamma hydrogens. Now you could then imagine, supposing we are able to remove one of these hydrogen atoms on the alpha carbon to form this molecule here. To form that anion, now we call this an enolate anion. Enolate anion. And then if you take a look at the enolate anion, one of the reasons why it is possible to generate the enolate anion from the alpha carbon instead of from the beta or the gamma carbon is because this enolate anion is stabilized by resonance. For example, we could move these electrons here to form a resonance contribution to that enolate anion. Now we have this. If you mind, we remove one hydrogen, we remove a proton from here, And that is how we form the, from here. That is how we form the enolate anion. Okay, so now we say this is an enolate anion. Now, if you then also look at the resonance structure, this structure right here, if you recall, a couple of chapters ago, we gave you an enol. We told you this was an enol. So that was an enol. So if you look at this enol here, you could almost think of enol as a vinyl alcohol. Think of it as a vinyl alcohol. So if you look at this enol here, and you look at the enolate anion, one of the resonance contributions from the enolate anion, you will see that the difference between this enol and this here is simply that this is the enolate anion here is a conjugate base of the enol, because all we've done here is to remove one hydrogen from here, and then we obtain this ion here. Okay, so therefore that is why we say the enolate anion could also be considered a conjugate base of an enol. Okay. Now, how do we generate the enolate anion or the enol itself? How do we generate enolate anion? There are two ways in which we could do it. Either through base catalyzed, generation, or acid catalyzed. Now let us now take a look at the base catalyzed generation of the enolate anion. Okay, we go back to cyclohexanol again. Okay. We have those two alpha hydrogens. Supposing we are in this solution that contains this cyclohexanol, we have hydroxide anion in form of potassium hydroxide or sodium hydroxide. What do we get? We get this. Get enolate anion plus, in this case, water. If you take a look at this reaction here, we know that the pKa, which is a measurement of the strength of the acidity of an organic molecule, the pKa for water is about say about 16. The pKa for this hydrogen here, the alpha hydrogen, alpha to the carbonyl, is about 20. Now, this is an acid-base reaction. For you to have an acid-base reaction, the direction of that reaction should favor the direction in which the reaction goes from the strong acid to the weaker acid. Okay? So we have water has a pKa of 16. This hydrogen here has a pKa of about 20. So which is the weaker acid here? Keep in mind, the lower the pKa, the stronger the acid, right? So which is the weaker acid? The cyclohexanol. Okay. So therefore, we will expect the direction of this reaction to be here. The reaction will go lightly in this direction. So it should be an equilibrium reaction. So we'll go here. Okay. So this is the stronger acid. All acid-base reactions go from the direction of stronger acid to the weaker acid. From the stronger acid to the weaker acid. So if I give you this equation and I ask you what would be the predominant direction of this reaction, you should be able to use the pKa value to tell me what the direction of that reaction will be. Similarly, acid-base reaction also go from, in this case, stronger base to weaker. Okay. Now, some of you will ask, okay, how come this hydrogen here, the hydrogen in the beta position, is not involved in this process? The reason why, because the pKa value for this here, this hydrogen here, pKa value for this hydrogen here is about 45 thereby. So it's a much weaker acid. Keep in mind, these are logarithm factors. Okay? So what is it saying here? This hydrogen here is about 10 to the 25 power stronger than this hydrogen here as an acid. And the reason for that is because of the, what is the reason for it? Because of resonance stabilization. That is possible right here. But that is not possible here. Okay? Okay. Now, if we want this equilibrium to go much further to the right, because for the most part, the reason why we are interested in the Enolate anion is because we are going to use this as a nucleophile. Okay, we are going to use this as a nucleophile to perform a variety of reactions very shortly. If you want this equilibrium to go all the way to the right, or much more so to the right, supposing we have this. We have the same cyclohexanol. Now, instead of using hydroxide, supposing I use this molecule here. This we call lithium diisopropyl. Lithium diisopropyl amine, and we abbreviate this as LDA. Okay, so for subsequent reaction, All I would do is just write LDA. You don't have to write the structure, but take a look at the structure here. It is much bulkier than the hydroxide, much bigger than the hydroxide, right? Now, if you want to perform this acid-base reaction here, what happens? We have this. We form the same enolate anion. And this diisopropylamine, this is a secondary amine. Okay? Diisopropylamine. Let me get this out of here. Now, why would this reaction go on more to the right than the hydroxide in the case of the hydroxide? Let's take a look at the pKa value. The pKa value for this amine is 35. And what is the pKa value for this hydrogen here? We say it's 20, right? It's 20. Okay, so what direction will the reaction go? Go to the right. Okay? So therefore, we could make a choice of a base in order for the generation of an enolate anion, depending on what we want to do. Okay? Give you some other bases that we can use. More examples of bases for generation of enolate. Anions. We could also use this. Keep in mind the purpose for us wanting to generate enolate anion is to use this as reagent in organic synthesis. Okay, we could use this alkoxide, for example. Okay, we could use the ethoxide. Okay, subsequently you will see me just write this. ET stands for ethyl. Okay? We use the ethoxide. In this case, you now form ethanol. Okay, the pKa for this is about 18. Okay, the pKa for this is about 20. Okay, so the reaction goes slightly to the left, but all we need for the most part is just some equilibrium. As long as you generate your enolate anion, then the reaction you will use the other reaction to drive the process. Okay, so we could use ethoxide. This is ethoxide. We could also use methoxide. As a base for generating the enolate anion. So you are going to be seeing examples of this as we move on during the course of this session today. Okay, so far I told you there are two ways in which we could generate the enolate anion. We could also generate the enolate anion indirectly using acid catalysis. Okay. Generation of enol, this time will be an enol by acid. Okay, let us take a look again at the cyclohexanol as an example. Supposing now we have say hydrogen chloride. Okay, you have hydrogen chloride and then you have a ketone with a non-bonding pair of electron on oxygen. What do you think will happen? What will be the first thing that happens? Okay, the non-bonding pair of electron on oxygen will abstract the proton from the hydrogen chloride. Very good. So you guys are beginning to know some reaction mechanism now. Okay. Happens. The oxygen now is positively charged. We still have this here, and of course the chlorine is here somewhere negatively charged. Now we see what is going to happen. The chlorine now comes in, acting as a base, abstract one of these protons from here, and releasing this pair of electrons. And in so doing, we are going to also release this pair of the pi electron to oxygen. So now we have at this point, we have formed an enol. Now we have formed an enol. So when you want to perform any further reaction using acid as a catalyst to generate the enolate anion, what you do is actually you do generate the enol. But this is what happens. Once you form the enol, okay, the enol is here. Imagine that you have the enol here. What this enol wants to do, ordinarily what it wants to do is want to rearrange itself. Back to the ketone form. This is what you normally do. Okay? I'm going to put this in brackets because this does not actually happen. Okay? But you could envisage that we are forming an enolate here. And this proton here is somewhere here. Okay? What really actually happened, the moment this comes here, this proton grabs the electron. So what you get is the ketone form. Okay? So there is always an equilibrium between the enol and the ketone. Indeed, if you take a look at this, both of them look like isomers. But because there is an equilibrium between them at room temperature, we do not call them isomers, we call them tautomers. So these are tautomers. These are tautomers. Okay, so this here, this enol and its corresponding ketone, they are referred to as tautomers. So this would be the enol form of the tautomer, and this would be the ketone form of the tautomer, because it goes back and forth. Now the point we made there is, once you form your enol, you form your enol, if by any chance, say you have, say some alkylating agent here. Say you have some alkylating agent here. While this is trying to go back here, grab the proton, what's going to happen? What's going to happen? Just while this transiting between the enol form and the ketone form, you form this in transient, and then simply it comes here before the proton protonate the enol form, the enolate anion, and you get what we have here as an SN2 reaction. And what you end up getting, you therefore get this product. So you end up with this product. Okay. So now what this now leads us to is the synthetic application of enols. Okay. Now we are now going to begin to discuss the synthetic application of enols. Keep in mind, the only reason that we have interest in enols because we can't use them synthetically to make our molecules. Okay. Now say synthetic applications of enolate anions. Okay, one. Say alkylation for example, like I told you before, like just giving you in that last example, supposing we have this, we have acetic acid acting as a source of acid, and we have this alkylating agent here. There at the same time, say benzyl iodide. Okay, what do we get? We get this. This would be a case in which this reaction is being performed under acidic condition. Keep in mind, under acidic condition, you form an enol, and then when the enol wants to go back to the ketone form, it forms in the enolate anion in transient or in transit, and therefore that then acts as a nucleophile. So you can see the limit of what we can use the enolate anion form is almost unlimited. It's just your own innovation or your own ingenuity will drive whatever you want to do with it. You can do just about anything you want to do with this type of molecules. Okay, so this is a case in which we form the enolate anion under acid catalyzed condition. We could also, under basic catalyzed condition, now under basic catalyzed condition, what you do, You do step 1, you add your base, in this case LDA, or hydroxide or methoxide or whatever base you want to use. Okay, in this case you must state step 1, step 2, because what you are forming here, you are actually forming the enolate anion. Okay, and then step 2, you just dump in your appropriate alkylating agent. Say for example we want to use this. Then we get this. Okay, okay, an interesting twist to this alkylation, either using acid catalyzed condition or basic catalyzed condition. Say for example, if you have this is still under alkylation. Say we have this here. Say I have this molecule here. And I do this. LDA, step 1, step 2, some alkylating agent. Give me an alkylating agent, Alonso. Any? Propyl? Yeah, propyl bromide. Propyl bromide, okay, good. Propyl bromide. If we do that, guess what we are going to form? This is what we get. This is the product that we are going to get. Why are we going to get that product? Why not? Okay, let me come back to this. Now, on the other hand, the same starting material, I do this under acid catalyzed condition. Okay, say I use acetic acid or hydrochloric acid, and then this I dump them together, right? This is also propyl bromide. This is what I will get. Now you begin to see the ingenuity of the organic chemist. We could actually engineer molecules to go where we want them to go. Now, and how does this happen? In the case of LDA, remember the structure of LDA I gave you was a big molecule, right? Now, if LDA wants to do this, the first thing it does is to come here to abstract this hydrogen. Because of the bulkiness of LDA, what it does is to come here, abstract the one that is more accessible. So this is because of steric hindrance. And that is why we get this product here. Because it does not want to, it's too much energy. If you force it to do it, it will. But why do it when you have other hydrogens here? Okay? On the other hand, in the case of this here, under acid catalyzed condition, remember under acid catalyzed condition, what do we get? We actually form this here. Change the color of my pen. If you recall, under acid catalyzed condition, I'm sorry. We actually form the enol, remember? Okay, with hydrogen here, with metal here. We form the enol. Okay? But the enol, if you recall the alkene chemistry when we did chemistry of alkene, whenever you want to form an alkene, the more stable, the more substituted the alkene, the more stable the alkene is. Okay, so therefore, the choice that you have to make if you want to do the acid catalyzed condition is, do we want to make this enol or do we want to make this enol? Okay, these are the choices. Let's say molecule A, molecule B. Those are the choices. But if you take a look at the two choices, molecule A, which is the enol here, will be more stable than molecule B because it is more substituted. So what drives this? What drives this here? This reaction here is thermodynamics. In other words, the stability of the enol product. That is what drives the process when you do the acid catalyzed condition. And so therefore, once you form the enol here, and then your alkylating agent will have no choice but to come right here. And that is why we form this product here. Do you follow that? Okay.
You
know, okay, you think about it later. Okay. You want me to slow down a little bit? Okay. Okay. Everybody got this? Okay, so now let's begin to see what we can do with it. This is just under alkylation, right? Okay. Now, okay, we are going to come back to alkylation. Okay. Other reactions. 2. Halogenation. Okay. How to do this? By the way, all of these reactions here, let me write this here. Enolate anions can be generated from aldehydes, so not only ketones, esters, carboxylic acid, and derivatives, and carboxylic acid derivatives. So there is really a world of chemistry here when it comes to enolate chemistry. Okay, so halogenation, so we could have this. We do it under acid catalyzed condition. We could have acetic acid and bromine. You get bromine, alpha bromination. You get the alpha bromination. We could do the same thing similarly with LDA and bromine. Sometimes iodine could also do it, and chlorine could also do it. So you could use this. We could actually use the concept of enolate anion to make alpha halogenated carbonyl compounds. Okay. Okay. Reaction number 3. Malonic ester synthesis. Malonic ester synthesis. Now, listen very carefully to this one. This is a big one. Okay, because you will get this in your exam, so definitely. This molecule here Okay, I'll make this ethyl. That's ethyl malonate. Okay. That is called ethyl malonate. Or sometimes referred to as malonic ester. Okay? Or malonic ester. If you take ethyl malonate and you take sodium methoxide or potassium methoxide, what do you form at this point? What are you going to form? With this here. What happens? Methoxide with this here. It will, okay, we are going to get an acid-base reaction. Okay, what do you think is going to happen here? We'll pull one of these hydrogen here. By the way, the pKa for this halogen here, the pKa for those halogens is about pKa for those halogens is about 11. So it's actually a lot more acidic than the alpha hydrogen of cyclohexanol. And why? Why do you think it's more acidic? Because it is between two carbonyls. Once you form the conjugate base, you could stabilize the enolate anion by resonance with two carbonyls. Okay? Okay. So what do we form? We get this. So now once you form your enolate anion, at this point you then dump in your alkylating agent or some kind of electrophile. Okay? You could now say that because this is an SN2 reaction, your alkylating agent must be primary or secondary. Exactly. Very good. Okay, we do that. And now what do we get? We get this. Okay, so now you form an alkylated malonic ester. You have now alkylated this carbon here. Now you could now take this. Okay, you could take this and hydrolyze dilute acid. What do you think we are going to get if we hydrolyze with dilute acid? You have an ester, two ester functional groups, and dilute acid. What do you get? What do you get? You get carboxylic acid. When you take an ester, you hydrolyze an ester. This is acid catalyzed hydrolysis. Okay. Remember Fischer esterification. This is the opposite of Fischer esterification. Okay, so now you get a dicarboxylic acid now you get a dicarboxylic acid Now look at the relationship between this carboxylic acid. If we say this is carbon 1, right? This is carbon 2, this is carbon 3. Okay, those carbonyl, they have a 1-3 relationship to each other. Anytime you have two carboxyl groups in a 1-3 relationship to each other, which we refer to as beta dicarboxyl, beta dicarboxylic acid. In this case, we say beta because in reference to this carbon number 1, this is carbon number 2 will be alpha, and carbon number 3 will be beta. So that is why we call it beta, using the Greek symbol beta dicarboxylic acid. Anytime you have that relationship, if you apply heat, you heat this up, okay? What is going to happen? Let me take this out of here. This beta dicarboxylic acid will lose a molecule of carbon dioxide just right away. Okay, and does it do that? You have this here. So you are going to get what we call decarboxylation. Once you apply heat, okay, so this one comes here, form a carbon-oxygen double bond, and in so doing, you are going to release this bond to here, and in essence, it looks like you are going to get this. And somewhere here, this hydrogen here is floating around. I just showed that just to show you exactly what happened. So I'm going to put the bracket around here. That's not really, you don't really get this enolate here, but it's almost like a fleeting, a transit enolate anion, and grabs this proton here. Just as this, you are losing this, carbon dioxide is gone. Just as you are also almost like you are spitting out carbon dioxide, then this proton here also grab onto this enolate anion that is being formed, and then finally you form this product here. Now you form this product. So what have we done? This process that we've done, in which we started with the malonic ester, we formed the enolate anion, we did the alkylation. This is alkylation right here. Okay, then we did the acid catalyzed hydrolysis of the diester to the diacid, and then we apply heat to remove carbon dioxide to eventually obtain carboxylic acid. This process, this reaction is known as the malonic ester synthesis. Okay, that process is called malonic ester synthesis. Okay, now the next process of the malonic ester synthesis is that you are forming a carboxylic acid. That is the next process, formation of carboxylic acid. Okay, so let me go ahead and formation of carboxylic acid. Okay, let's give some more examples of this. What time do we have? Oh wow, we got plenty of time. Okay. Okay. Okay, now let's give some more examples of this. Okay? Of course, you start with malonic ester, right? So you start with malonic ester. Then I do this. Step 1. Okay? Generally, when you start with malonic ester, the base that you use to form the enolate will be the ethoxide, because you have ethoxide in the ester. Okay? Okay? Then step 2, depending on what you want to use for your alkylating agent, keep in mind this is an SN1 SN2 reaction, so they must be either primary or secondary substrate. Okay? So you decide, okay, I want to, let me use a different color here. Okay. And then step 3, you do hydrolysis. And then step 4, you apply heat. Now what will be the product? What will be the product? CH2 attached to this here. And one of these hydrogen is done, right? Okay, so therefore you form this. So now you form this here, let's see. Okay. So now you actually form this. That will be your product. This here, even though initially we lost one hydrogen when we formed the enolate anion, okay, so how come we now have another hydrogen at the end? Can anybody tell me? If you look at the mechanism, remember, right here, this proton came here to add to after you lost the carbon dioxide. Okay? Okay, so you actually form this. So this is a very good way to form carboxylic acid. Yes.
How many carbon atoms do you supposed to have in the product?
Okay, this here, no, don't forget, this here will be gone after the hydrolysis, right? And this here will also be gone when you lose the carbon dioxide.
Yes.
You see, how many carbon are you supposed to get? Okay, this here is this.
Oh, yeah. Okay.
Right?
Mm-hmm.
You see it?
Yeah.
Okay. And this carbon here is this. Okay, and then of course this, you only have one carboxyl left because you lost carbon dioxide. Now supposing we want to do 2 alkylation. Supposing we want to do 2 alkylation. Start doing malonic ester synthesis again. Step 1, ethoxide. Okay, what do you get there? What do you get at that point? Enolate anion. Okay, very good. Then step 2, you add your alkylating agent. Since we want to use ethyl bromide, let us go ahead and use that. Okay, now you do step 3. Okay, after you form that alkylation, I say, okay, I want to do another alkylation. I do ethoxide again. Okay, you follow that now, right? You follow that? Or you want me to give it to you?
Yes, please.
Okay, okay. Okay, so at this point, this is what we form. This is what we have. Okay? And now, I say I want to do another alkylation. Step 1, ethoxide. So what am I going to do here? The enolate on which carbon? On this carbon, right? Right? Okay. So once you form enolate on this carbon, then you could do another alkylation. Say I want to add another alkylating agent. Okay, I want to use benzyl iodide. Okay, so now what do I get? I get this. Okay, you see that so far? Right? So now I've done 2 alkylations. Now, at this point, now what do I do next? To finish my malonic ester synthesis, what do I do next? Hydrolysis, exactly. Now I do hydrolysis. Now it has to be acid catalyzed hydrolysis because you must form the carboxylic acid. Okay? So now we have this. And what do I get at that point? Okay, now what do I do now? I apply heat, exactly. Okay? And therefore I will now get this. Okay, now I get an alpha substituted carboxylic acid. Okay, I find a way to, oh, I'm sorry, this should be CH2 right here. I'm sorry about that. Okay. So you see what we can do with the malonic ester synthesis. At this point, we alkylated the malonic ester synthesis twice, and then after we do the decarboxylation, because carbon dioxide is giving off here, we do decarboxylation, then we get a carboxylic acid. Okay, so that's reaction 3. I'll give you one more reaction. I know you guys are getting tired, and then we'll leave for today. Okay, so anyway, you can see here there is so much we can do with this, and we are really have not scratched the surface yet. Okay, so let us reaction number 4. Aceto-acetic ester synthesis. Aceto-acetic ester synthesis. In this case, what do we have here? This is what we have. This molecule is called ethyl acetoacetate. Or just referred to as acetoacetic ester. Okay? Now it is the same concept as in the case of malonic ester synthesis. The difference here now, we are going to get a ketone. Okay, let us see what happens. Ethoxide, right? We use ethoxide because we have ethyl ester here. So, which one of these carbon will be abstracted to form the enolate? This carbon, this hydrogen, or this hydrogen? The middle hydrogen. Why? Because it's more acidic, right? The pKa for this is about 11, and the pKa for this is about 20. Okay, so this is a lot more acidic than this, so therefore the enolate will be formed on this carbon. Okay, so let us, okay, so we form the enolate. Okay, at this point, you want to add an alkylating agent. Okay. Abra, what kind of alkylating agent do you want us to use? Huh? Metal, okay. Okay, methyl iodide, right? Okay, good. Let us use methyl iodide. Methyl iodide, okay? And therefore, we are going to form this product here. Oh, I'm sorry. Okay, so we now form an alkylate. We've alkylated ethyl malonate. I'm sorry, acetic ether. So if you want, we could do dialkylation. Okay, if that is what we want to do. Okay, but let us stay with the monoalkylation at this point. So now what we want to do now, we want to hydrolyze the ester to the carboxylic acid. Okay, once again, take a look at the relationship between the carbonyl. Let's call this carbon 1, right? 2, 3. So there is a 1-3 relationship between this carbonyl of the ketone and the carboxyl group. Anytime you have a carboxyl group, has a 1-3 relationship with any carbonyl. If you heat that sample, carbon dioxide will be given off. Okay? So this is a beta keto, what we call a beta keto acid. Beta keto acid. In other words, if you say this is carboxyl group, is the carboxyl group of interest, carbon number 2 is the alpha carbon, and carbon number 3 will be the beta carbon. So that is why we call this beta keto acid. Okay? Now if you then take if you heat this up, okay, what is going to happen? You are going to spit off carbon dioxide. Comes here. Comes here. In essence, you will be forming like a, you put that in bracket. You'll be forming like an enolate. So you have this. Oh, I'm sorry. That is, so that will be done. In this case, this carbonyl will be gone. We have this here, and then you form almost like an enolate right there. And next to that, just imagine that the proton is just waiting around to capture that enolate anion. Okay, and so therefore, what does it give you? You end up with this metal comes from your alkylating agent, which is right here. Okay? This was your original, this here, this carbon here, what's this carbon? Okay, we have 2 hydrogen here, because at the end, when we lost the carbon dioxide, this proton here is adding to this. Okay? So you do lose carbon dioxide. Okay, so what we're giving you here is what we refer to as the acetoacetic ester synthesis. And what is the net process? The net process is the formation of a ketone. Okay, the net process of the acetoacetic ester synthesis is the formation of a methyl ketone. Formation of a methyl ketone. Okay? And let me give you a few examples of acetoacetic, because what I've done here, I give you the mechanism. So examples. Okay. Of course, we start with the acetoacetic ester. Okay, we just say step 1, hydroxide. Step 2, we could use the alkylating agent. Let's just say we use this here. Okay, this is bromide. Okay, do you want to do another alkylation? Just one alkylation, okay. And then 3, what is step 3? Hydrolysis, very good. And step 4, heat, right? And so what do we get? We get this here. Let's use this green for green so that we know the difference. This is the alkylating stuff. Okay, so we get this. Attach to that. So now we see here, this here is this. This carbonyl is here. Of course, this methyl is this one here. And of course, we know that this one came from, this here came from this alkylating agent right here. Okay? Now, to make things a little bit more interesting, supposing, and I'll take this. This is the last reaction, then we could go. I've got 10 more minutes, but I'll let you go. Oh. To make things a little bit more interesting, supposing I do this. Hydroxide in the presence of iodoform. This reagent here, what does it do? We do step 1 and step 2. What does it do? It does convert a methyl ketone to a carboxylic acid. So therefore, because if I give you a carboxylic acid, say give me a synthetic scheme for that, that doesn't necessarily mean that you are doing malonic ester synthesis. It could very well mean that you did acetoacetic ester synthesis, and then you follow that up with what this reaction is called an iodoform reaction. This is called iodoform reaction. Okay, so I will see you guys on Tuesday, and we will continue. When we come back on Tuesday, please watch some of the webcasts. When we come back on Tuesday, we will be working problems. Okay? Yes,